we're covering, as you've probably noticed, we're covering a lot of, very important stuff today, right? So this is a very high, utility class. The final thing that I would touch on is the problem of scaling up. Right? We're in the days of big data, right? So how about running the algorithm that we've seen so far, any one of them on big data? Here's what's going to happen. You start it running, and then you die. And then one day, towards the end of the universe, hopefully before the entropy death of the universe, the answer comes back. And what is so? We need to worry about scaling up our algorithms. In fact, people sometimes say that data mining is machine learning scaled up. I think that's a little bit understating it, but certainly in practice, a lot of what people, like me, did in the early days of data mining was take machine learning algorithms that were like cubic or quartic or whatever, and try to make them linear or log linear, or maybe even better. But try to make them scale to large data sets. And this was not easy. And there's been a progression, with different algorithms and whatnot. These days we can scale a lot of these things to very, very large data sets. And what I would like to do is just, in 5 minutes, briefly touch on what some of these things are, just so that you're aware of them. Okay? So first of all, what is the biggest reason why these algorithms will not scale to large data? The biggest reason, of algorithms like ID3, which does, pre-pruning, C4.5, which does post-pruning, is that they all assume that your data fits in main memory. They do random access to the data. Right? I put my examples in main memory, and then I go collect statistics of different attributes in random orders depending on how the tree is growing. Right? But big data doesn't fit in main memory. Now, main memory keeps growing, but big data grows faster. Right? And Moore's law is great, but the Moore's law of disk actually far outpaces the Moore's law of computing. This is actually a lot of what drives machine learning and big data is this thing, is that our ability to store data greatly outpaces our ability to process it. If the exponential for processing power, if Moore's law moved faster than the corresponding law for disk, well, big data, well, just shove it into the CPU and run it, right? The problem that we have, there are complaints like, oh, I'm a company, I have, terabytes of data. But, what do I do with it? I'm limited by being able to process it, right? So, moral of the story, when we mine big data, we're going to be mining it from disk. And number one, reading data from disk is, roughly speaking, 1,000 times slower than reading it from main memory. So already there we have a problem, right? We just suffer the 1,000 factors, slowdown. But the other big thing, of course, is that what? What is the big difference between disk and main memory? In disk, access is sequential, right? So if you take an algorithm, like ID3, and try to run it on disk, it's never going to finish unless the data set is very small. It's trying to run, I have a data set of, 1 billion points, which is not unusual these days, or, even 100 million. And it's randomly accessing, the disk is spinning, the head is finding its place, and this never finishes. So, the number one thing that people worried about doing when, scaling up became a big issue, this was like circa, 1995, let's say, was can we have algorithms that only do sequential scans of the data? I want an algorithm that, reads the disk and maybe picks the roots. And then maybe reads the disk again and finds the entire next level all at once. And then keeps on doing this. Okay? This is a natural idea, but making it work and actually gaining efficiency is surprisingly tricky. There were a series of algorithms that did this, which you should at least know about, with names like Sprint and Slick and whatnot. IBM actually had a data mining package at one point. They're one of the first companies really, out the gate with this, and this was basically one of the main algorithms that they used there. Now this works up to millions of examples. The reason it doesn't work beyond that is that even just reading 1 million examples from this takes a while, particularly if they have a lot of attributes. So you're already looking at, if you were doing multiple scans of the data, this thing may be taking, days or weeks, even to just learn one model. But of course, the learning process is that you don't learn one model. You are playing with the data and learning a model in 20 different ways and doing cross-validation here and picking parameter there and not changing the data like that. And if your cycle of this is a week or even days, you're in trouble. So the next thing is, and this is really what's sort of like the dominant paradigm today is we are going to require what's called working in data stream mode. Data stream mode, and this gets us back to that distinction between batch and online learning, right? Data stream mode is, I only look at the data once. I see it and it's gone. I see the next one and it's gone. It's gone. I can choose not to use it, but if I want to use it, I have to use it right then, and I never see it again, right? This could be because I can't afford the disk storage, or because I don't want to scan the disk more than one time because it would take too long. Somebody had...
Yeah, I said you don't store it anywhere either. You just see it once.
Exactly. So this is one option, is the data is never stored. For a lot of very high volume applications, like say network monitoring, right? You're an ISP, right? Your servers are like, your routers are generating, are spewing out data, like crazy. You don't even want to store them, right? In some cases, however, you can afford the storage, right? But just running through that, because storage is getting cheaper and cheaper, but just running through that takes too long. Okay? So the third generation of algorithms are algorithms that work in stream mode. They do at most one scan of the data. In fact, ideally, they don't even scan all the data. Okay? And for that, again, there's a number of different algorithms, but the best one that I know of now is something called BFDT, very fast decision tree learning, which was actually invented here at UW. So you should be suspicious because it's me telling you about my work. So you should probably get a second opinion on this one. But you can go to Google Scholar and whatnot, so Nevertheless, it's good to know that there are algorithms, without getting into all the details of how this works. We have algorithms now that can actually, grow a decision tree in one scan of a data that is basically as good as the decision tree that you would learn with random access. And in fact, the best part of this is that you might need much less than a scan of the data. You can actually be scanning the data and decide at some point that hey, I've already grown as much as I'm going to grow. I don't need to see any more data. I am done at this point, which is a very nice thing to have. Okay? Again, we're not going to go into the details of these algorithms here, but you want to be aware that they exist, because if you find yourself pruning a very large data set or even a large data stream, these are probably the kinds of things that you want to look at. You certainly need to understand, the basic algorithms first, and that's what we spent our time on here. But, you don't want to have the experience like I know people who have had that. They started, with ID3, and they spent, 6 months basically, rediscovering how to mine from disk. Okay. Questions? All right, very good. So now your fun begins. Now you're going to do your project where you implement the decision tree learner and apply it to clickstream data. Don't do the project at the last moment, because it might not finish running before the due date. This is not like some of your other projects. You have been warned. Do it this weekend and let it run until the due date. Is one option. Well, if that needs to happen, then you're doing something wrong. We carefully selected subsets of the data that are reasonable enough for what you want to do. But nevertheless, we hope you have a lot of fun with it. All right. See you next week.